Welcome everyone to Optimizing Training Workloads on GPU Clusters from Together AI. I'm Lucian, Product Manager.
And I am Ryan. I am on the engineering team.
In our agenda today, we're going to tell you about the way we're going to do this is first cover tips for cluster planning. What do you need to know to plan your GPU cluster for training? Then we'll spend some time to talk about validations for pre-training. It's really important to validate your pre-training so you're ready to start training as soon as your cluster is up and running to minimize onboarding. And then we'll talk about the optimizations for your training. And we'll do that with some live examples with the optimizations. So let's get started with cluster planning.
All right.
All right, cluster planning. So in cluster planning, first of all, oftentimes you may wonder, how do I get started? How do I size my cluster for training? What type of GPUs? How many GPUs do I need? How much storage? How much memory? And so here, I think, first and foremost, one aspect comes to what type of model do you plan to train? Is it going to be language, text, image, video, robotics, biology, others, right? And next is your data set. What is the data set size that you have? And that will give you requirements for storage, for example, as well. We always recommend to start small and then size up your training. So try an environment and then scale it up. And that's for cluster sizing. Bring your data to your cluster is important. So copying your data set, how large is your data set, how much time it's going to take you to copy it to a location, and is also part of your planning. And next is about choosing between Kubernetes, Slurm, and so forth. And so first question would be, what are these, what do they mean? So what is Slurm? Slurm is an open source workload manager and job scheduler that's designed for Linux clusters, and it's widely used in HPC environments. It allows you to manage and allocate resources like CPUs and GPUs, and schedule jobs based on various policies and priorities. It supports a wide range of plugins and different functionalities. So that's one, you may be familiar with Slurm, especially if you're coming from the research background. If you're more from the enterprise background, you're probably familiar with Kubernetes, the open source container orchestration system that automates deployment, scaling, and management of containerized applications. And so that supports a wide range of container runtimes. It's not just Docker. And it gives you self-healing capabilities, resource management, service discovery. And so today we'll show you some training example with Kubernetes. When you have Kubernetes, you can, on top of that, use what we see commonly is KubeRay or TorchX. So KubeRay, for example, is an open source project that integrates Ray with Kubernetes. And so Ray is another high-performance distributed computing framework that makes it easy to scale your applications. And so KubeRay allows you to manage Ray clusters on Kubernetes. If you are using PyTorch and you need a PyTorch native platform for launching and managing distributed PyTorch applications, then there's TorchX. And so TorchX, can be used as well with conjunction with Kubernetes. So we'll deep dive into that a little bit more. So that's a consideration. And here the true, recommendation is choose what you're familiar with or what your background is with, and there's optimizations you can do with all of these. Drivers and CUDA versions. So this is important. Drivers for NVIDIA, CUDA versions for the libraries. So typically there would be release notes, bug fixes, and so forth. So depending on what hardware you train with, if you're on Blackwells, you would need a certain version of drivers in CUDA. If you're on on Hopper, it would be different. So that's for cluster planning. Ryan, anything you'd like to add?
I'll just point out that all of these choices are made fairly easy on Together instant clusters. So go try out an instant cluster. They're pretty cool.
Yep. On instant cluster, Ryan, so the, together.ai/instant, and you can log in, create an account, and if you click on GPU clusters, you can create a cluster. And for example, today, we're going to use an instant cluster for our training. Now let's tell you about pre-training validations. So all about pre-training, we see it in two umbrellas. So one is your cluster access, how you get access to your cluster. What is your, are you going to use your cloud console? Are you going to use a CLI? And then all the other parameters, kubeconfigs, Kubernetes API, Kubernetes dashboard, how to check for your control plane and data plane, nodes, and then all the commands to run. So that's cluster access, number one. Number two is all the commands you can run to actually do your validations. So really important to make sure that the cluster you receive once you've created your cluster or you get access to your training cluster is that everything is to spec before you start training. So hardware is hardware is compliant with what it's supposed to be, it's properly functioning, and then that you can start training. So you don't get slowed down or unexpected errors for training. And that's really in a nutshell pre-training validations. And I just saw a question, by the way. I mean, I saw two questions. One is, which one do you recommend, Kubernetes or Slurm for training? And so, I would say the one that you're most familiar with, if you have one you're more familiar with, or what your background is. Ryan, what do you think? Say if I don't know anything about Kubernetes or Slurm and I need to train, do you have a recommendation on how to start with the least amount of friction?
Yeah, definitely. It depends a bit on your goals, but if all you want to do is trading and you want to get started quickly, Slurm is probably the way to go. Slurm has been around for a long time. There's a ton of great documentation about it. It's a really easy way to get started. In contrast to that, if you have some goals besides training, like maybe you're running mixed training and inference, Kubernetes might be a better choice in that case because it's easy to host, like web applications, API servers, and this sort of thing that could go along with your inference setup. Likewise, if you plan on doing a lot of automation, or that sort of thing, Kubernetes kind of really shines in those areas. So that's what I would say. Slurm's great to get started. Kubernetes is great for flexibility.
If you also think in your journey that you may be doing some inference as well, in addition to training, then and your greenfield in either Kubernetes could help you because it would allow you also to do some inference as well. So that may be another consideration to have. One more question. We have a question here that says, can you start a small cluster on CPU and then move to something that's more involved with the GPUs?
We don't support this in instant clusters today, but I like the thought. One of the things we recommended before is start small and scale up. Of course, for most of the training jobs that you'd be running, you would need some kind of CUDA kernel. So from a software perspective, it might be difficult, if your goal is training a model, it might be difficult to start on a CPU-only cluster because you would be missing CUDA and some of the expected software for that. But that being said, you can certainly train a model on CPU. It would generally be a much smaller model. So if you're just looking to poke around, that could be a interesting thing to do, but we don't support it on instant clusters yet or today.
We don't support that yet, and what we traditionally see is folks validating workloads potentially on CPU first, but with instant clusters, you can create a cluster and use it for a very short period of time. So that's also something where you can just validate that you have um, proper functioning of a GPU system. Let's move forward to our next slide. So the three key optimizations that we want to talk to you about rely into these three pieces here: the CPU, GPU, the storage, and the failure recovery. And so we'll really show you these live, I think, with training. So Ryan, would you like that we do you want us to get started on some demo?
Yeah, let's show some things. So we'll jump into some of these pre-training validations, and also we'll have a look at training a model, doing some of these optimizations. We'll walk through the process, and there's certainly more than one way to optimize the model, but I'll show you kind of the broad things that I look at first, and then we can narrow in as we go. So to get started with some of these pre-training validations, this window I'm sharing now, this is K9S, which is a front end for Kubernetes. And I have it logged into my instant cluster. So over here, we can see this is the instant cluster that we've spun up on Together platform. We're running 565 NVIDIA driver. It has CUDA 12.6 on the system, but within our container on Kubernetes, we can use different CUDA versions if we wish. We also have a terabyte of shared storage attached to it, which will be really helpful when it comes time to train a model. So what I want to do quickly is I've spun up a debug pod, and in this debug pod, I can go do some of these pre-training validations. So, before we kick off a training run, I think it's good practice just to kind of take a look at the systems and make sure that everything looks the way we expect. So one of the first things I usually would run is just NVIDIA SMI. I can see here that I have 8 GPUs in this system. They're NVIDIA H100 GPUs, which is expected. Another thing that I'm looking over here is this 0 in the last column. This represents if there are any ECC errors on the GPU. Sometimes GPUs can be recovered from an ECC error by rebooting. The GPU does a process called row remap, and it can map the memory around the wherever that error is. But we can see all of our error counts are 0. So these GPUs are healthy. This system is looking good from that first pass. Another thing I usually look at quickly is the system topology. So I'm going to zoom out a little bit because there's a really cool table that this prints out for us. So this is an NVIDIA SMI command as well. But the thing that I'm mainly looking at here, when we're training a model, we need the GPUs to all communicate with each other, and we want that communication to be as fast as possible so that our training performance is good. So I'm looking at these link between every GPU. So we can see in this table, like this is GPU 1 and GPU 0. They're linked with an 18 NV links, which is great. That's the expected value for an H100 system like this that has these NV links. And then also, I'm looking at the InfiniBand adapters, which we have a little legend down here at the bottom. We use, in these systems, there's Mellanox adapters both for the InfiniBand network that we'll be using for GPU communication, but also for the Ethernet. So there's eight of these adapters are InfiniBand adapters. There's 12 listed here, but 8 of them are InfiniBand adapters. And there's a one-to-one correspondence with the InfiniBand adapter and each GPU in the system according to the system's PCI topology. So that's something we could get super deep on and talk forever about, but we'll just keep this a little high level today because we have a lot of stuff to cover. The main thing I'm looking for quickly in the topology is that I see there's on some of these network adapters, this PIX, which down here at the legend says we're traversing. Yeah.
Yep.
Traversing at most a single PCIe bridge. So kind of a quick glance at this shows me that these network adapters kind of line up to the GPU system topology. So that's what I wanted to look at there. And then we can also go have a look at the adapters as well with IBstat. So IBstat's part of the Mellanox driver package, the OFED package. And we can see if we were to look in here, we're looking at this link layer InfiniBand. Rate is 400. That's 400 gigabytes per second NDR. State is active. Link is up. Sorry, gigabits per second. And there should be 8 of these that are all active. So if I were to do something like IBstat, grep InfiniBand, and count them, well, apparently that didn't work.
Lowercase
spell it wrong. Maybe I just spelled it wrong. Wow, I cannot type.
And so this system is, here we have H100s, SXMs. And so a server has 8 H100 GPUs, and those are the NV18s that we see in the map, in the topology map. And here you have, I think now 8, correct, in your IBstat, so 8 InfiniBand.
Yep, should have used case insensitive grep. The B was capitalized. Anyways, that's kind of the things that I just would quickly check for. And this debug pod that I've created, you can see there's actually 2 of them. There's one for each of the nodes. Oh, there's another quick thing to check for, which is that all of our nodes are ready in Kubernetes. So on this instant cluster here, we have 2 GPU nodes. So we have 16 GPUs in total because each of them have 8. And then we have these 3 control plane nodes that are running the Kubernetes services.
Okay.
But they're all ready. They're looking good. Let's get into training. What do we say?
Let's get into some training. Yeah, great.
Let's do it. Okay, so one of the things when I made these debug pods, I requested.
And what you mean, Ryan, by debug pod, for those unfamiliar with Kubernetes, this helps giving basically a Linux terminal and logging in onto your server to be able to actually see what's happening. So your storage environment or anything like that. Is that what you mean, Ryan, by a debug pod?
Yeah, essentially exactly that. It's just a container that I can get a shell into and run some commands. But because the commands I was going to run requested, I wanted to check on GPUs, I wanted to check on InfiniBand, these debug pods actually request resources from Kubernetes. So if we see here, I've requested 8 InfiniBand devices and 8 GPUs for each of these debug pods. And so these debug pods are consuming those resources in Kubernetes. So we have to delete them in order to be able to train because we need our GPU and our InfiniBand devices for training, obviously. So I'm going to go ahead and delete these, and we can kick off a training. The other thing before we, you know what? I have to delete the replica set. Kubernetes self-heals, so if you just delete a pod without deleting the thing that controlled the pod, it comes right back. So another thing that's interesting is we need a place for our data. Lucian mentioned this a bit earlier. So I went ahead and created a volume ahead of time here. So this volume we can see is 100, or sorry, it's about a terabyte volume. I made it 1,000 gigabytes. I probably could have made it 1024, but I was thinking in base 10 when I did this. And the access mode is RWX. And so this is important as well because when we're training, we need to share a volume between all of the pods that are doing the training, because we're going to do distributed 2-node training. We're going to be using all 16 GPUs. And those GPUs are set up on, with the InfiniBand and able to communicate with each other, they need a place to read the training data set from, to write their checkpoints to, and each of those debug pods will need that capability. So this access mode RWX means read, write, many, which means that this volume is able to be accessed by multiple machines multiple pods at the same time. This could say RWO, for example, if it was a different storage class, which we're not using here. But if you do happen to be training on Kubernetes, this is one of the problems you could run into. If it's RWO, then only a single pod can access that volume at a time. That's not what we want for distributed training. So we have a nice RWX pod here that we can use. And it looks like we have a couple of questions here.
Yep, we got a couple of questions, exactly. And the first one here is the debug pod best practice? And really the answer I'd say to that is yes, specifically when you're looking at optimizing and tuning your training to get the best performance. But I would say beyond that, once you're training and you know your environment, you don't necessarily need it. But Ryan, what do you think? Do you always do it when you train? What do you recommend our audience?
I start with a debug pod. As the process goes and as I get into a good workflow, I may delete my debug pod and throw it away. And if I need it again, I'll just recreate it again. But I do always start with a debug pod. And I start with a debug pod for a couple of reasons. One is I want to be able to check on the systems quickly. And two is a point Lucian mentioned earlier, is that we need a way to get data into our cluster, like our training data set. We need a way to get data out of our cluster. Maybe we want to back up our model checkpoints to some object storage bucket or something. So it's really great for kind of data ingress egress as well. So I actually have several pods here. And while we're talking about this, we have a great question that I'm going to go a little out of band here, which is, what is the definition of a pod? This is great to answer before we continue talking about pods. But a pod in Kubernetes is a container. So it's very much like actually a pod can be a group of containers, but it's very much like a Docker container. So in this case, our Kubernetes clusters are running containerd, not Docker. But if you've used Docker containers before, these pods are basically isolated ways to run pieces of software, whether that software is a shell, like I was doing in my debug pod, or when we launch a training job, the training job will also launch in a pod. So a pod is a very kind of base unit of software orchestration that Kubernetes uses to describe a group of containers. And I spin up a couple of debug pods for different purposes, actually. I have the debug pod I showed earlier was one that requested GPUs, so I could go inspect the state of the GPUs. I also have two pods here that you can see. Traffic is an ingress controller, so that's not one. That comes with the cluster. But Ryan GPT data, spoiler alert, the model we're going to train is called Ryan GPT. But I have a pod that has our data volume mounted. So I usually would use a pod like this for, if I go into it and I can see that I have this data volume that is 1,000 gigs. I can go look around into my data volume. I can see, the files that training will make. There's some checkpoints here already from previous training runs. I also have in code, I have some stuff here where I can edit code directly in the Kubernetes cluster, which is very handy for, kind of iterating quickly. And I'll add a philosophical point here, which is, I want to get to optimizing. And when we're talking about optimizing, one of the things you should really strive to do is to make your iteration cycle as short as possible. So we want to be able to test, get results back, change something, test again, get results back. And we want to compress that time as short as possible, so that we can quickly get good results from optimizing. I think that's true in optimizing and debugging and probably life in general. So that's what this build kit pod is for. Build kit actually in this pod, we have also the data volume mounted, but this has the code that we'll be running for our training. And I can build the Docker container here. I can use it to make changes. I can get kind of very quick iteration from this build kit pod. So
great tool, great tool. Brian, do you mind just opening up our instant cluster webpage where you're yes, perfect. And we had another question about our Kubernetes instant clusters, and do they come with K9s actually pre-installed? And so the first thing I wanted to say, K9s is not pre-installed, but Kubernetes is pre-installed. So that was the first thing I wanted to cover. And actually in here, when you create your cluster, you can see directly your kube config. If you click on that kube config and you copy it locally, then you can just connect with kube and directly interact with it. And then we also have a Kubernetes dashboard pre-installed as well. K9s is fairly straightforward and fast actually to install on the command line. So Ryan, I don't know if you can help us here with that. I know it takes you a couple of seconds, but
yeah,
you can share with the audience. Yeah,
definitely. So K9s is it's a Kubernetes client. It's generally something that you would run locally. So for example, I'm running it on my laptop at the moment. But the kube config is what lets me connect to the Kubernetes cluster. So that's kind of the two parts. The Kubernetes cluster is in the Together cloud, and K9s is running locally on my laptop, and this kube config contains the connection info so that K9s can talk to Kubernetes.
Great. Let's get into training. Thanks, Ryan.
Yeah, let's do it. So we'll be using TorchX and Volcano and Kubernetes to train today. There's a lot of different software stacks you could train with, whether Kubernetes or Slurm, or even on Kubernetes, KubeRay we've seen is a lot of people training on that, and there's a lot of different ways to do this. So this certainly isn't the only way, but it's a way that I like. And what Volcano is a gang scheduler, which means that when we submit a job to a Volcano queue, it will wait to schedule the pods until all of the pods can be scheduled together, which is really useful because we don't want, maybe 9 out of 10 pods are available and 1 is blocked. We don't want to schedule 9 pods that are waiting on the 10th, and then now we've got 9 extra pods blocked, right? So we want them to schedule all at once or not at all. And that is what Volcano gets us. It's a very useful thing. Slurm behaves like that by default. So if you're using Slurm, Slurm will not schedule your job until all of the resources are available to schedule your job. And the other thing we'll be using is TorchX. So TorchX is essentially a way to write some code around how you launch jobs. So this is useful again for iterating quickly, for making changes and launching another job and making changes. And then once we're ready, then of course it can all be automated because we've got it as code. So TorchX is pretty cool too, but I think it's officially a PyTorch project. But in any case, we'll be using Volcano and TorchX to launch our training. So there's a couple of parts of this. We have our training script, which is basically just a Python script that is going to load some data.
Got one more question before we get too deep into this.
Sure.
Can lens be used for training? And here I would assume that the person is asking for lens as a tool or a library for GPU training. So there's this Kubernetes IDE that's developed, I think, by Contena that's called Lens. And so that can be actually, it's designed to work with Kubernetes. So I think, I personally haven't encountered much, but there's no, it seems pretty possible here to just use it with Kubernetes. Yep.
Awesome.
Go ahead, Ryan. Thank you.
All right. Yeah, so about our training code, this is essentially kind of toy training code here that we're going to optimize. And we're training a GPT-2 based model named Ryan GPT, as I alluded to before. See another comment about PyTorch job.
Mm-hmm.
Do you also use Kubeflow trainer? Is there any advantage of using TorchX with Kubernetes? To some degree, I think a lot of this comes down to personal preference.
Mm-hmm.
I don't have anything particularly good or bad to say about any of these stacks. I've seen them all work, and if there's one you're already using and you don't necessarily have a good reason to switch, stick with it. I mean, they all seem good.
Yep.
We use MPI, Java MPI operator as well is pretty good. There's a lot of good options out there.
Great. Let's get back onto our training, our Ryan GPT.
Yep, let's do it. All right. So this is a GPT-2 based model, which is a fairly small model by today's standards. It's like 124 million parameters, and pretty basic training code. We're going to load a data set. We're going to do some training, and we're going to see how it goes. So the other part of this is we have a script. This is the TorchX part. We have a script that's going to actually launch our training job here. So this is, the other thing was the code to run. This is the specification of how to run it. And in here, we have some important things. We have the Docker image we're going to use, the script we're going to use. This J parameter in TorchX is kind of analogous to like make -J or the compiler flags, but in here it says 2 by 8. So we're requesting a distributed training run on 2 nodes with 8 GPUs each. That's what this J parameter means. It's a little bit terse of a name. And we can set up some environment variables here as well. These two are probably 2 of the most important environment variables that you will see when it comes to running a distributed training job with NCCL. NCCL is an NCCL, NVIDIA Concurrent Communications Library. And what we see commonly is training performance might be bad because of some issue with the network fabric that NCCL is using to communicate. And that's one of the first things to check, I think, if you're debugging a training performance issue or trying to make sure you're running, optimally. So these 2 environment variables, NCCL socket IF name, we have this set to ETH0. This should be set to the Ethernet fabric or some kind of management fabric. This NCCL socket IF name is where NCCL is going to do its orchestration. So it's going to kind of set up the ranks and figure out who's going to be talking to who on the compute fabric. So this is really kind of separate from the compute fabric. You can run it on the compute fabric, but I like to have this separate. So I've set this to run on ETH0, which in our cluster corresponds to the Ethernet in-band fabric. So just like the management, regular Ethernet fabric. The other one that's important is NCCL IB HCA. So we want our actual compute traffic to be on the InfiniBand. So we've got our management traffic on Ethernet and compute traffic on InfiniBand. And the way that I've specified this here is to say basically not ETH0. So we're not using the same, we're not using compute over the Ethernet. And we're saying not LO, which is LO is the loopback interface. So this is like localhost. So we obviously don't want to send compute traffic over localhost. We would rather send that over NVLink instead. So that's how I've specified these two variables here. You could specify them other ways, like you can manually list out the adapters to use for nickel. So this could be like a list of the 8, MLX50, MLX501, all the adapters that we care about. But in our case, the only InfiniBand adapters on the system are the ones that we want for our compute traffic. So this is a perfectly fine way to specify this.
Right, and this is really important for multi-node training, right? When you're actually going outside of one server of eight GPUs to another one. So we want to make sure that we're using actually the InfiniBand 400 gig network versus going through the Ethernet or PCIe buses. Have you seen this as a common error or performance in multi-node? This optimization that you talk about?
We do see this all the time, and especially if you are doing some training on Kubernetes, maybe you have this set on the system, but inside your container has a different set of environment variables. So this is one of the points that, making sure this is set up correctly is, can be a little bit tricky at times. We pre-configure a lot of this stuff for you on the Together Instant clusters, like on the system, it's pre-configured. But within Kubernetes, because you write your own pod spec, this could be set to anything. And so it does come up a lot. And the symptom that we see is your training run won't fail. It just runs really, really slowly because we're sending, 8 GPUs worth of compute traffic through too small of a pipe. So that's one of the first things to check when it comes to kind of optimizing a training run, getting good training performance.
Great. Sorry, go on.
Oh no, did you have something?
No, I was wondering if we can start maybe to run the training, or if there's more you want to share with us before jumping right into it.
No, let's run it. The only other thing that I wanted to share that's kind of important is the resource requests here. We have a great question in the chat that I'm excited to show as well. So we'll get right to that. But the resource requests here, it's important that our pods are requesting the GPUs, requesting the InfiniBand devices. We also request CPU and memory. This is how the Kubernetes scheduler knows how to place these pods. So it's very important to tell, and even our mount, we have to say like our data volume. So all of those things are setting up our job with Kubernetes. So the cool thing about Torchex, or one of the things that I like about Torchex, is that our code to launch a job is just a Python script. So I'm going to go ahead and run it just like I would run any Python code, and it's knows how to talk to Kubernetes already, which is very cool. I'm going to go ahead and hop out of this shell, and we can see now I have 2 pods running, which is awesome. There's
training.
There's a Volcano job, VC job, Volcano job that is controlling these 2 pods. And if we go we usually want to look at the rank 0 logs. Most training code is set up with some extra output on rank 0, but we can go watch the logs and actually see our training run happen, which is pretty cool. So this is doing, kind of its setup. There's 2 pods, as you saw. There's a rank. They give you a, pod number and I forget exactly what these numbers correspond to, but the other one will have a 1 and a 0. So we're setting up our data set here, and it's going to start training here in just a moment. So this is the exciting part. GPUs are heating up, so love to see that. And this is always what I'm looking for right here.
There we go. The time.
Yep. So we can see our training progress here. This is a fairly short training job. Now, if we were to, once we've optimized, what we would probably do, as I was talking before about increase or decrease your iteration cycle. As we optimize, what we'd probably do is maybe run a little bit longer jobs and queue up jobs so that when one job finishes, the next job starts. But because we're optimizing, we're not gonna queue anything up right now. We're just gonna kind of run a short run, change some stuff, run a short run, change some stuff. So I can see this, we're like halfway through this training run already. And you'll notice that it actually, it stabilizes a little bit. So the units here are seconds per iteration. So we can see, kind of the first one is like 6 and then we're 4, and then it kind of drops down. Looks like we're, in the 3.6, 3.7, 3.9, maybe 3.7 is a good average, just eyeballing it. 3.7 seconds per iteration. So thinking about this a little bit, seconds per iteration, a smaller number is better here. We want this number to be as small as possible, I guess. If it was inverse iterations per second, we would want a larger number. So our goal when it comes to optimizing really is how small can we get this seconds per iteration number? We want this to go as fast as possible. And there's a little bit of output here that's from the training code. You can see average time per iteration is 3.84 seconds. Average speed is 0.260 iterations per second. These are just the inverse of each other. So, and our total training time, total number of iterations, just a little bit of useful stats for us. So we had a question in the chat about how do we diagnose slow communications and do we use a profiler? I think in general, yes, we use a profiler, but the approach that I like to take for optimizing is kind of a metrics first approach and look broadly, look at like system level, look for any kind of obvious signs of trouble on a metric side, and then to get into like Torch profiler, using a profiler to get some more detailed information about where exactly our training code is bottlenecked. So it's kind of a start broad, cast a wide net, and narrow in approach. And one of the things that we can detect fairly easily from our dashboards are exactly this question. So how do we detect slow network performance? So this is the Together cluster dashboard. We have 2 dashboards with our clusters that we're constantly using. They're both extremely useful. And this one represents the whole cluster. So we're looking at all the nodes on our instant cluster. And then our other dashboard that we use a lot represents an individual host. So this individual host here is one of the GPU nodes. You can see there's kind of this lump in GPU utilization. This is our training run that we just ran. And, the GPUs were sitting idle. We launched a job. The GPU utilization went to around 100%. There's a little bit of a dip here. And then a couple of GPUs dipped here. And we finished it around 100% as well. Worth noting that this is a fairly short training run. The whole thing only took 2 minutes. So our sampling is very short here. Part of that is because we want to decrease our iteration cycle. Part of that is because when you're demoing something, you don't have much time to wait. So in reality, maybe we would want a little bit longer sampling because there's only, during this 2-minute iteration, I think samples are collected every 15 seconds here. So there's a small number of samples is what I'm getting at. But we can see our training run there. We can see GPU memory utilization. Here's something else quite interesting. So we have a lot of headroom in our GPU memory utilization. These are H100 GPUs that have 80 gigabytes of memory. And we're only using a very small fraction of it. The InfiniBand stuff. So we can see here some metrics about InfiniBand, port transmit, port packets, but actually on our cluster dashboard, we have a very useful InfiniBand chart, which is this. It's not just InfiniBand, it's all of them. This is network throughput in kind of human readable units. And so we can see here that our network throughput, and if we look at these, our network throughput, it looks like 2 GPU nodes, and both of them say Ethernet, which is, we can click on this and we can see there's InfiniBand on that spike, but we're actually using much less InfiniBand than we are Ethernet. This is immediately suspicious. Usually in a training run, what you would see is that the InfiniBand fabric is seeing more traffic than the Ethernet traffic. So we can, kind of zoom in on a section here if we want to get more details. But yeah, as we hover over those, we can see like almost a gigabit per second on our Ethernet. And the InfiniBand is using a very small bit of traffic. Now, that doesn't definitively tell us that that we have a slow network or we have some network issue, but it gives us a clue. It gives us something very suspicious to look at. And this is part of why I like this metrics-driven first approach, is because we can look at all of these things, we can correlate them in time. We can see, kind of, here's our spike in GPU power draw, GPU temperature, so on. If there was like an InfiniBand link flapping, we would see during that period of usage, we might see that there's like this InfiniBand link down counter going up. And in this case, there's no InfiniBand link flapping. We don't have like an overheating transceiver or something causing an issue, so this chart is just blank. But if there was an issue there, we'd be able to see that in time. This chart here is also super interesting, CPU IO wait. So as we're debugging the cause of our slowdown, we might see low InfiniBand traffic, but it could be that it's correlated in time with high IO weight.
CPU. Mm-hmm.
And what that means is that we're starving our GPUs of data, or we're not able to get data into our GPUs fast enough. So that essentially tells us that something needs optimizing with our data loader, something needs optimizing with our their data volume, or we're storing the data, or we're doing something not optimal with how we're getting data into the GPU. That's what that would tell us. And so this metrics first approach gives us this kind of big picture, holistic idea of what's happening on our system. And then we can narrow in, and that's really where the profiler shines. So we did see, and actually if we look at CPU IO weight here, it's only at 2%, and it's on the control plane nodes, it's at 2%. On the GPU nodes, it's like 0.007%, very low. So IO weight's not our problem here. But if we start with metrics, we could see, if these things were correlated, we can rule that in, rule that out, and then we know kind of where to focus our efforts with the profiler, where to start digging deeper. And the host dashboard also likewise gives us some kind of more detailed information about what's going on. I'm going to expand my time window here because our training run went out of scope. A couple of things that I usually look forward to is kernel context switching. So right now we're at around 22,000 operations per second during our training run. That's a pretty normal number. What we mean when we mean context switching, if we have, perhaps we spun up way too many threads, we would see a very high level of context switching here, because the kernel's like constantly having to switch between this thread and that thread's execution. And so that switch, the context switch, has some overhead to it, and this could be something that could cause us a non-optimal training run. We have disk IOPS, disk usage, Lots of great, memory stuff here. Tons of great metrics on these dashboards. So that's usually where I start. Gives me a very good idea at a whole system level of where I want to start looking closer. A lot of times, training performance problems can be diagnosed and solved right from one of these dashboards in a short period of time. And we might make an adjustment to the number of threads or so on. So yeah, that's usually where I like to start on those.
Now, would you make a change on the threads, or what would you do here, Ryan, to try to speed this up?
Yeah, good question. So in our case, I don't see a high level of context switching. I don't see high CPU I/O weight, but I do see, if we go back to the cluster dashboard, I do see that we have a lot more traffic on the Ethernet than we do on the InfiniBand, which is a bit suspicious. But we do have some traffic on the InfiniBand on one node. Why is it only on one node? Again, a bit suspicious. So the next thing that I would probably do here is start debugging this network throughput thing, because I'm not seeing any other correlated problem. If we were waiting on disk, the network could also be light, but I'm not seeing any correlated problems. So it might be that our network is just misconfigured itself. So
you configured the network in Kubernetes, right? The mapping of the devices.
Yeah, that's right. It was this set of environment variables in our launch job script. So I set nickel IBHCA to this and nickel socket IF name to that. Maybe this isn't the way that I want to go about this, or maybe the InfiniBand devices aren't working. So this is where I would go back to debug pod. So
Let's do it.
Yeah, let's do it. We only have a few minutes left, so we'll see what we can get done. So the reason I'm launching a debug pod here is because now I want to go look at the actual InfiniBand devices on these nodes. And maybe just in the interest of, figuring out if I'm misconfigured, what I'll do is, instead of specifying it the way I specified it before, I'll specify it by directly specifying. So I want 5.0, I want 5.1, and I can go look through this list and figure out exactly all of the adapters that I want. And I think I have a command I'm pulling up really quick on my other screen that will get me the list. Oh, that's not going to work. Okay. We'll just do it manually. So I want, what I'm looking for here is InfiniBand. I want 0, 1, 10 is Ethernet, 11 is Ethernet. So I want 0, 1, 2, 3, 6, 7, 8, 9. Okay.
0, 1, 2, 3, 6, 7, 8, 9.
Yes.
Let's see if we got those. Zero, 1, 2, 3, 6, 7, 8, 9. And if you don't need to memorize these, we also provide you documentation on our website, for example, for InfiniBand settings. So this is in our documentation as well.
Yeah.
All right, 0, 1, 2, 3, 6, 7, 8, 9. Great.
Nice. So let's run it. Oh, I apparently deleted a comma at some point. All right, so I need to, for my we can see here my Volcano job is stuck as pending because I still have these debug pods that are consuming GPUs. I'll delete those. We will go back here and we should get, as soon as those spin down, the new ones will spin up. And basically what I would be watching for here is if the network sort of, let's look at the last 30 minutes here, if the network pattern changes. This is our last training run. We'll run the next training run. We'll see if something changes. These might take a second to shut down for some reason. Sometimes Kubernetes does some cleanup. Here we go. New ones are running, so hopefully within a minute or something we should be seeing the changes. And while we're waiting on that, maybe
we can do some questions.
Yeah.
Some questions, and then also give some conclusion thoughts. One is here about the profiler. Can the profiler track the GPU I/O weight while training, as the CPU may not be well utilized during training?
Yeah, that's a great question. I assume so. Off the top of my head, I don't know exactly how to do that, but I would assume so. When we're using a profiler, we instrument our code to collect what kind of data that we're interested in profiling. So we usually will instrument our code to suspicious code blocks. We'll kind of wrap in some span that we can tell how much time it took to do that thing. And we can combine that information with metrics as well. So if there's coming from the NVIDIA drivers or coming from something, we can see if, there's during the span of data loading, the GPU I/O weight was high. I don't know if that's a specific metric served by the driver or not. It's not something I've looked at directly, but generally speaking, when we instrument our code to kind of watch our data loading, watch our our all reduce, or kind of watch whatever various operations that we're doing in our model, and that'll give us some idea about each of the pieces. So really, the profiler can help us narrow in on exactly where we can even see this section of code is where we're spending all of our time. And yeah, it's an interesting point. CPU may not be well utilized during training. We see that a lot. It a lot depends on the model. Sometimes some models are legitimately CPU bound, even though they're trained on GPU. There's a lot of different types of models out there.
Right. So let's see if we got some here results on training.
Yeah, it's looking like InfiniBand is still our pattern is looking about the same so far. It's just early result. Whoops. So that might indicate to us that we did have our configuration correct, and maybe InfiniBand traffic is low because we're training a very small model. It's a 124 million parameter model. So it very well could be that it just does not take much traffic to send this. And actually, kind of looking at the numbers here, 114 megabits per second. So on the order of the size of our model, interestingly.
Yep. Great. Well, maybe we can give some summaries for folks, and we'll see if we get some more live results. But really, thinking about optimizations, remember about those three sections that we had. Think about the CPU, GPU, the storage, the failure recovery, and we really like with Ryan the observability first approach. Monitor what you can. There's a lot of tools out there. It's very simple to get observability going in your cluster. You have a Kubernetes dashboard also, an instant cluster that's spun up. So look at the environment, use a debug pod, and then start tuning. Understand the model and look at CPU, GPU. If it's storage bound, look at storage performance. If it's your shared storage, your PFS, look at. You could do maybe some FIO testing there to see what the expectation is. So the scope is pretty broad. but with a little bit of organization and a debug pod, that will go a long way. Ryan, anything else to share on that? Any other best
Thank you.
practices? Thank you.
Yeah, thank you all for joining. That's really what I wanted to share.
Thank you, everyone. So remember, we have instant clusters. You can go and sign up and actually spin one up and use it. We have some documentation, a link here in a Discord, and be also on the lookout. We'll be following up with some more blogs, some more and some more collaterals online. So thank you, everyone. Have a great day.